Okay, the next chapter is intermediate code generation, and this is the next task that is performed by compilers. So after semantic analysis, an intermediate code generation is then performed. So why we need an intermediate code? An intermediate code. So this is the very important code. That is, as its name implies, it is a code that is generated before the target code is just generated from the source code. So in between the source code and the target code, another representation is required, and that representation we call it an intermediate code. So that intermediate code generation is very important in the translation process, the compilation process. We just classified the first three tasks as front end tasks, and the last three tasks as back-end tasks. So the front-end tasks are the lexical analysis, the syntax analysis, and the semantic analysis. And the last three tasks which are considered as back-end tasks are the intermediate code generation, the code optimization, and target code generation. So in a compiler, the front end translates the source code or the program into an intermediate representation, and the back end generates the target code from this intermediate representation. So in between the source code and the target code, there is an intermediate representation. So that from that intermediate representation, then intermediate code is then generated. So the use of machine independent intermediate code is just important to retarget another machine. So it is helpful for retargeting another machine, and it is also important for optimization. So optimization can be done on the machine independent code, and then the target code is generated. So in practice, the intermediate code generation and type checking can be done at the same time, as both use syntax directed translation. So both are using the syntax directed translation. So the translation of the type, the source code into the target code is directed by the use of semantic rules and the type checking rules for the semantic rules that are helpful for performing type checking. So for performing the intermediate code, for just generating the intermediate code, the compiler can use the same syntax directed translations and generate the intermediate code, from the syntax tree, which is just embedded with the set of instructions, or the translation schemes, set of rules specified as in the form specified in the form of translation schemes. So while generating the machine code directly from the source code is possible, it entails two problems. It is possible to generate without having an intermediate code. It is possible to directly generate target code from the source code, but this is just creating two problems. One, for example, with M languages and N target machines, we need to write M front ends and M times N optimizers and M times N code generators. So if we have M languages, language 1, language 2, language 3, language 4 up to language M, and we have target machines, N number of target machines, machine 1, machine 2, machine 3, machine up to machine N. So if we are not generating the target code from the intermediate code, we need to create for those M languages and N number of target machines. We need to develop M front ends, that is M number of lexical analyzers, syntax analyzers, and semantic analyzers, because here those are language dependent, and M times N optimizers. So if optimization is not just performed on an intermediate code, we need to perform or create optimizers that is M times N. So the number of languages multiplied by the number of machines. So this much number of optimizers are required to be developed, and similarly M times N number of code generators we need to develop. And the code optimizer, which is one of the largest and very difficult to write components of compiler, cannot be reused. So optimizer cannot be reused. So machine and language dependent. This is a machine and language dependent. That's why we need to develop M times N optimizers and the code generators. So they are just language and machine dependent. So by converting the source code into an intermediate code, the machine independent code optimizer may be written. So machine independent code optimizer can be developed. This means just M front ends, N code generators, and just L optimizer. And optimizer can be developed. So we can have only the such number of tools that can be involved in the translation process. So when we have an intermediate code, if we are just generating or creating an intermediate code in order to reduce the number of tools to be developed and involved in the translation process, the intermediate code must be easy to produce and easy to translate to machine code. So the intermediate representing that intermediate code should be easy to produce and easy to translate to the machine code. So for just having an intermediate code with such feature, we may use sometimes the sort of universal assembly language. So an intermediate code is sometimes represented by universal assembly language, and that intermediate code should not contain any machine specific parameters like accessing the registers of the machine, like the addresses, and any machine specific, that is machine dependent parameters should not be existed in the intermediate code, because that intermediate code should be represented and independent of any machine configurations or machine features. So the intermediate code should be free from any machine specific features, so that it can be easily producible and easy translatable machine, representation, so that we can easily generate the target code from the intermediate code. So we do have other forms, some classical forms the classical forms of representing the code as an intermediate code. So we can create quadruples or triples or three address code or abstract syntax tree or directed acyclic graph as some forms of intermediate code. So any code that is represented in any one of those forms can be considered as an intermediate code. So what are those forms? Let's see. For example, we have assumed in a given source program, assume we have the statement, that is represented as a plus, then b times c minus d over b times c. Assume we have such a statement in a given source program. So before generating the target code from this source program fragment, we can just create an intermediate representation, either as three address code representation, as quadruple, or as triple, or as syntax tree, or as directed acyclic graph. So for the statement like a plus b times c minus d over b times c. So if we have such expression in a given source program, this line of code can be represented in one of those intermediate code representation forms. So if we represent this expression as a three address code, we can just consider, for example, so it is just represented as a plus, this one is a plus b times c minus d over b times c. This is the instruction, the expression in the source program that is required to be represented in an intermediate representation as an intermediate code. So when we are representing this expression as the Sri address code, here Sri address code is just nothing but it is a type of an intermediate code in which at most 3 operands can exist. The maximum of 3 operands can exist, just including the result operand. So if any expression in the source program is having more than 3 operands, we need to break down that expression into sub-expressions, each with maximum of 3 operands. So in our example here, a plus b times c minus d over b times c, there are 1, 2, 3, 4, 5 operators, and there are 1, 2, 3, 4, 5, 6 operands. So the variables are operands, and we have those mathematical operations. So the operands, the number of operands in this expression is exceeding the number of operands allowed in Sri address code representation. So as our expression is violating the Sri address code representation, this expression cannot be directly considered as the one represented in the form of Sri address code. So it is a long it is just violating the Sri address code representation, because there are 6 operands used. So we need to break down into sub-expressions, each not violating the Sri address code requirements or criteria. So when we are representing a given expression in Sri address code, we simply generate the temporary storage variables, that can store then intermediate values. So for example, we can consider the first temporary variable t1, like t1, to be assigned the first product b times c. Look, this is a sub-expression that is valid as per the conditions of the Sri address code representation, because here we have 3 operands t1, b and c, 3 operands possible. The result is assigned on t1, and the operands on which the operator star is applied is b and c. Then next, another is just once we represented the first b times c, next we can just create another temporary variable t2, which will hold the sum of a and the product b times c. We have already calculated the product and assigned it on the temporary variable t1, so we can say t1 here. And the next is calculating the product, another product. So t3 can be assigned the product B times C. Again, this is Sri underscore representation, and another is just the temporary variable T4, which will hold the quotient D over B times C is already calculated and assigned on T3, so we can say T3. This is also correct as per the requirements of temporary, the Sri underscore representation. And finally now we can assign the difference between the first part and the last part. Here we can assign the difference on T5 as this, the whole part is assigned on T2, so we can say T2 minus this whole part is assigned on T4, so we can say T4. So this is the Sri underscore representation that we have created. And the quadruple is just quadruple is a tabular representation having 4 columns, as its name implies. Quad means 4. So a quadruple is another form of intermediate representation that is using 4 columns. That is a tabular representation having 4 columns. The columns are corresponding to the operators column, the first argument column, the second argument column, and the result column. So once we converted an intermediate representation of a given statement, just once we created the Sri address code representation of a given source code fragment, we can refer that Sri address code representation and create quadruple. For example, from this Sri address code we can create a quadruple by taking each sub-expression of the Sri address code. So for this one we have those 5 rows, for corresponding 5 rows of the quadruple. So the first operator is the multiplication. The first argument is B, the second argument is C, and the result is T1. The second is the operator is plus, the argument is A, then the second argument is T1, and the result is T2. And the operator is star. Here the first argument is B, the second argument is C, and the result is T3. And so in this way we can create the quadruples, and the triples can be considered as the optimized version of quadruples, because here in triples we just remove the result column and use only 3 columns. Try means 3, so 3 columns. So only 3 columns are used in triples. Then the question that can be arising is how the result of the previous expression can be referred. So here, as you can see, each row is assigned an index, just similar to the way of indexing an array. So from 0 we just start assigning an index to the first row, incrementing by 1. So if any result is required in the next rows, we can refer the result from the previous row by this index. So that's why, for example, in row 1 we refer the previous product from row 0. So this in bracket 0 indicating that we are just referring the result of the first row, which is the product of B and C. And similarly in row in the fourth row, that is indexed or by 3, we are referring the result, the previous result from row assigned index 2, from the previous row, that is the product of B and C. So in the fourth or in the last fifth row, we are referring the result of row 1, which is the second row, the sum, and the third result, third row result from the fourth row. So we are applying the subtraction operator on the two results. So we can say the triples representation is the optimized version of the quadruples. And the syntax tree, another form of an intermediate code, is syntax tree. Syntax tree is just the graphical representation of the given expression, So as when we are just creating the syntax tree, the root of the tree should be an operator that is evaluated at the last step. That is, an operator with the lowest precedence level will be considered as the root of the tree. That's why here, as you can see from this expression, the subtraction operator will be evaluated at the last. Subtraction operator is evaluated at the last. That's why it is considered as a root of the tree. So to the left and to the right, so we can consider, like for example, to the right of this one, here we have this sub-expression and another this sub-expression. So the next operator that should be considered as the parent is the plus, because from the two, plus and star, plus is having the less precedence. So the operator with less precedence will be given priority. That's why we are just assigning this node the plus. So to the left and right of the plus operator, we have the variable a and the two variables which are applied, the multiplication operator. So now we can create A at the left of the plus, and on the right we have the multiplication, and for the multiplication the children are B and C. So in the same way, for the right wing of minus we have multiplication and the division and multiplication. So as they have just have the equal precedence, we can just take from the left associative. They are left associative, so we can take the division. We can take the division first, then we can add on the left wing of division D, then multiplication, then for the multiplication we can B and C. So this, for constructing syntax tree, it is good to consider the precedence level of the operators, so and their associativity type. So syntax tree is just a hierarchical structure of the given expression in which the operands are considered as parents or internal nodes. As you can see here, the parents are minus, plus, multiplication, division. So in syntax tree, operands are terminal nodes and operators are internal nodes. And another form of intermediate representation is directed acyclic graph, or simply DAG. So this directed acyclic graph can be also used as another form of intermediate code. So what is DAG? Here we can just simply state DAG as a minimized or an optimized version of the syntax tree. As you can see here, this directed acyclic graph is generated by reducing or eliminating this wing. For example, from the syntax tree, as this B and C, the product of the two B and C is already calculated on another wing of the tree. We can just simply remove this part, and we can refer the product from the other wing. So by removing this part, we can minimize the storage space. Similarly, the computational cost, that is the calculation cost, can also be reduced. So this DAG is an optimized version of syntax tree. So those are the some forms that we can use as an intermediate representation. Another form is postfix. So postfix is also considered as an additional form of an intermediate code. So in addition to the three address code, the triples, the quadruples, syntax tree, and DAG, we can also use postfix notation as an intermediate code. So postfix notation is practical for an intermediate representation, as operands are found just before the operator. So it is a type of expression in which operands are just placed before operators. So for example, for the expression, for the infix expression 1 plus 2 times 3, the postfix notation for this expression will be 1 1, then this plus should be shifted to after 2, and this star should be shifted to after 3. That's why we have 1 2 plus 3 star. So just we can use postfix notation as another form of an intermediate code representation. So 3 address code, most of the time we use 3 address code representation as a form of intermediate code. So the general form of this 3 address code is X assignment operator, Y, then another operator, then Z. So the maximum number of operands allowed is 3, X, Y, Z. So we have maximum those 3 operands. The operands can be 1, operand can be 2 or 3. So if it is more than 3, we should break down that expression so that we can have other sub expressions individually, not violating the requirement or the conditions of 3 address code. So in the representing a code in an intermediate representation, we can use those one of those representations: the 3 address code, the triple, the quadruple, and the DAG and syntax tree. So the postfix notation 3 address code, just the linearized representations of the syntax tree. So for example, if we have statements like non-assignment statement, assignment statement for binary operation, we can write simply X equal Y operator Z, just what we have done in our previous example. So T1 equal B times C, so the operator is times, then our in our case Y is B, then Z is C, and X is T1. So since those individual sub-expressions are not violating the 3 address code, then we can consider them as an intermediate code of the given expression. So for assignment operator and assignment statement of unary operator, like minus y, we can just have such assignment, because still this one is not violating the 3 address code condition. So X equal minus Y, possible. Like we can write an expression like T1 equal minus 2, possible. Copy statement is also written in a 3 address code representation as X equal Y, is just copying the Y value onto X onto X variable. Unconditional jumping can be represented by the keyword goto and the label L, and unconditional jumping. So without checking any condition, we can let the flow of execution jump to L. Conditional jumping, we can, if we have such conditional jumping in our source program, we can represent that conditional jumping in 3 address code representation as if X is the condition that is tested, and if the condition like x a relational operator, y. This is condition. So if this condition is true, then we can let the flow of execution jump to level L. This is conditional jumping, because this jumping is done only if this condition becomes true, if the condition x relational operator y becomes true. And functional calling statement, what if we have function calling statement in our source program? So if we have function calling statement in our source program, we can represent the function calling statement as an intermediate code in three address code representation as list of parameters. So we can just list or separately put the parameters like param x1, x2, x up to xn. Then finally we put call, then the function name, then the number of parameters we specify. For example, if we have like add comma, if we have the function like add comma x comma y comma z, if we have such function calling statement in the source program, then we can convert this into three address code representation, three address code as param x, then param y, then param z, Then finally, since we have only three arguments passed to the function, then finally we can specify call. The function is add, then comma, the number of parameters 3. So this is the three address code representation for the function calling statement add x, y, z. So this is how we can represent the function, any function calling statement in the source program. And any indexed arguments, so x assigned y 1 is an index, the first element, so we can assign the variable x the y, the first element of the y, the y at the address y plus 1. So x will be assigned the value at the address y plus 1. So the value at the address y plus 1 will be assigned x. So we can assign the address of the value on x which is available at index 1. We can also just simply change the value, assign the value of x on the y indexed by the value L. Simply L is representing the the I indexing, representing the index or the slot number of the array y. Then the address and operate pointer assignments. We can also use the pointer assignments. So obviously, as we can recall, the way we can use pointers. So x assign the address of y. So that means if we have already had a declaration of pointer x to assign the address of y on the pointer variable x, we can do like this, and this is just not violating the requirements or the conditions of C address code. And this is a variable value assignment, so the value of variable y can be assigned on pointer variable x. So the pointer variable value can be modified by assigning y. So those statements are not violating the C address code representation. So if we have such small statements, they can be written as they are specified in the source program. If they are just exceeding, then we should break down into sub-expressions. Now, let you consider those expressions as an exercise. Let you just work on those expressions and generate C address code syntax tree, C address code and syntax tree. So we consider this one. Our previous example, we considered this one. We considered the third one. So let you work on those the remaining part. And here, what is a different? What makes this one different from our previous example is just it is explicitly specified here. The last sub part of the expression is in bracket b times c, so we should give priority for b times c. So this will be having the highest precedence in the bracket, and division will be having less precedence. So let you work on those expressions. So if we have C program or a C++ program, like int a equal 3, b equal 4, then dot prod comma I, those are declaration statements, and dot prod equal 0, then for I equal 0, I less than 10, I plus plus, dot product plus equal a times b. So this program should be converted into C address code as an intermediate code. So just dot prod equal 0, we can just consider as it is, I equal 0 as it is, because the for loop should be converted into conditional jumping and unconditional jumping. So unconditional jumping and conditional jumping, we can not just directly write the word for in the intermediate code. So when we are converting this for loop into an intermediate code, this for loop is converted into an intermediate code by considering the conditional jumping and unconditional jumping. So since the condition is I less than 10, so we should think of the point or a step at which we should stop. We should stop iterating or looping, and we should also think of the point at which we should exit from the looping statement. So the previous statements, the assignment statements, can be written as they are specified in the source program because they are not violating the source code. But here, for the looping statement, here, we can just change into like level 1 the conditional jumping if I greater than 10. So we are just here putting the exit condition, go to L2. So go to L2, do nothing. If this condition, if it reached at the exit condition or the upper bound, otherwise it will perform temporary creating temporary variable. T1 equal a, T2 equal b, then T3 equal t times T2. Here, this one, this statement, which is the body of the for loop, should be break down into sub expressions. Why? Because this expression is just violating the 3 address code, because we do have here how many operands, 1, 2, 3 and 4, because this short representation is equivalent to dot product equal dot product plus a times b. So that's why we need to just break down this expression into sub expressions, each not violating the 3 address code conditions. So T4 will be dot prod plus T3. So once we calculated the product of A and B, then we can add that dot product with to the dot product, and then assign the sum onto variable or temporary variable T4. Then dot product then assigned. So this again, because here the dot product value is then modified, so dot product then T4. So finally then T5, because here we are incrementing the value of I, so T5 is holding the value of I after this incrementation. So after incrementing the I value, we can assign T5 and T5 then I, because here I means I equal I plus 1. Then go to L1. This is unconditional jumping. So without checking any condition, we can let the let the flow to be again diverted to, without continuing to L2, we can directly divert to L1 without checking any condition. So direct diversion to L1, it then again checks the condition. If this condition is false, it continues working on those statements and again moves back to L1, and if this condition is true, that means it reached the exit step. So we then move to L2. On conditional jumping, it is directed to L2. On unconditional jumping, it is moved back to L1. So in this way, we can convert any C program or C++ program into intermediate code. So you can just consider those statements, C statements, and just analyze those statements. So those are the additional examples so that you can read. So let you read about those statements and work on those examples. Thank you.